So let's continue. So we are about to characterize something in general. So we finished by defining a class, which is denoted by this purely or stylized D, which contains all the functions, and the functions are the smooth market clearing mechanisms. The meaning was given a price in P and given the bit theta of a player, how much the player gets. That's the sum of those D's of all the players has to be the total resource. So the requirements for that, of course, each D is a smooth market clearing mechanism. That's one. The second is that for any positive size of resource for all those functions, all valuation functions which fulfill the requirements, a price anticipating user's path, so when the user anticipated the bit influences the price, is concave. What it means is that the function, the value of what the user obtains because of obtaining the resource, when the amount of resource the user obtains is the function d of her bit and of the price, which is in turn the function of the bit and of the mechanism b, because price anticipating user. So that's how much the user obtains. Minus how much she pays, because we are talking about the path, the total utility. What she pays is what she obtains times the price, which again is a function of that's the price. That's the utility of the user, which she gets minus what she pays, and this is concave in theta r, in the theta in the bit of the user. Now, for any number of users and for any vector of the bits of the other users, this function is concave on the domain of the strictly positive reals if the bit of other users is zero vector, because there's zero vector, because then we don't want to have this complete zero vector. Therefore, we look on positives. And if the bit of value is a non-zero vector, then we allow theta r to be zero. It could be any non-negative vector. Third, given any price, we can just achieve any amount of resource. Given any amount you want, there is some theta such that what you get when you bid theta given price p is exactly d. You can always achieve that. That's kind of this onto requirement. And the last requirement, which is that for any positive price and for any non-negative bit vector, the d is always non-negative. So all the users only get something, or nothing. They never have to give. Now, requirements besides the last one, which seems trivial, and the first one, which is basically these smooth market clearing mechanisms, which tells how much the user with bits theta gets when the price is p. Besides those, basically 2 and 3 seem reasonable, and we're now going to explain why they're here. But still, they seem kind of unusual. Like they don't seem the exact requirements we need. Why those? Why not others? No, the answer is as follows. So they are justifiable, as we'll see soon, and they are exactly what we need. Well, that's exactly the, you may say, technical meaning of that we need. And since that's justifiable, that's what we assume. That's kind of the intuition you may have. At least that's one of them. Of course, that's only intuition, and you don't have to have any intuition. You can may have any, once you are good with the mathematics, with the theory, you may have any intuition you want. I'm just giving you one possibility. So we look just at what we used to do, the proportional allocation, and we show that that's one of the cases of that mechanism. So that allocation is in calligraphic. That's one of the capital D's in this curly D, in this curly D. Why? Well, first of all, we have already seen it's a smooth market sharing mechanism. Maybe I should remind you what a smooth market sharing mechanism is. It's basically smooth market clearing mechanism. Not sharing, clearing. It's a differentiable function which tells how much you get when you have a given price, the first variable, and a given bit, that's your bit, the second variable. And in the case of what we have, it's basically the bit divided by the price. That's what we, that's D. And also there is this unique price which makes it exactly all the users get exactly the C. That's also what we have seen. Now, when the price is all zero, it's not clear what the user gets given some bit. So then the price is then first of all the price is undefined, and that's not required, because only when it is not zero the prices should be. Oh, excuse me, I've confused. When theta is zero, the price is undefined, and that's fine. That's the consistent of the same mechanism. However, the prices are zero. Okay, D is not defined over, so it's okay. D is defined over all the positive prices, so it's fine to divide by price. Okay, so as I said, our original proportional sharing is exactly it's one of those smooth market sharing mechanisms, market clearing mechanisms. I apologize when I say market sharing instead of market clearing. And the mechanism simply that the function is d of price and of bit is bit divided by price. So how much you want to pay divided by how much a unit costs, and that's exactly how many units we get. And that fulfills all those requirements. Okay, so let's continue. So we see now that it's actually something in this calligraphic D. So first of all, as I said, just now it's a smooth market sharing mechanism. Second, you need to show concavity now of the user pair. When the user is price anticipating, so the user realizes that the price depends on the theta. And the reason is that for the case where the others don't beat only zeros, we have already shown that's concave. That was an exercise. I can show you, I think, that exercise. That's 17.4, page 459 in the book. And now for the case when the others do beat only zeros, then it's also concave, because if you beat something positive, then you get all the resource in that, because the others beat zero, minus what you beat. Whereas if you beat zero, we just define that what you get is minus infinity. That's how we define that in this case. That was not how we defined it then, but it's still fine. It will still be concave. It's still a concave one. Now, the third property is that you are able to achieve anything, and of course, when what you get is the theta divided by the price on some positive price, you are definitely able to achieve anything. Simply, you need to beat price times what you want to achieve. And that's exactly what you need to beat. It's also intuitive. You can achieve anything if you given a price, then you may beat anything. Anything non-negative, you may achieve anything pre-chosen non-negative. And the last one, of course, you always get a share of resource which is non-negative. So the proportional allocation, what we did, is indeed one of those mechanisms in this class. Now, let me just, as promised, justify the conditions we have. it does not tell why only those. I assume that as I said, it will seem to be enough for the theorem. Now the concavity condition, that's something which is often used to guarantee non-emptiness of Nash equilibria. So it's reasonable to assume that, and then we'll need to characterize the Nash equilibria using only first order condition. So that's kind of a commonplace condition. We may assume, it's reasonable to assume that. I'm not claiming, of course, that always the case. That's an assumption, but that's a reasonable assumption. Now, condition 3. Let's beat condition 3 is that you can get any share you want, and that's exactly that. The bid can cause any demand at any market clearing price. It's expressive enough. That's the condition. And condition 4 means that a user never supplies, only gets something. It can never be that your demand is negative. So these conditions are reasonable, and we'll see that they allow for interesting conclusions. Very interesting. First of all, consider a class of mechanisms in this digraphic D, which generalizes what we have. So what we have is theta divided by p. Here it's theta divided by p to the power of p to the c. Or in other words, theta times p to the power p is in the power of 1 or minus 1 divided by c. So it's p, in other words, it's theta divided by p to the power of 1 over c. Theta divided by the c root of p. For some c which is this 1. Now for c equals exactly to 1, it's going to be theta divided by p. Exactly what we said. Now, not only for c equals to 1, but for any c which is at least 1, it's easy to see that this d is in digraphic D. You can take it as an exercise. So all those are in the class. Now, what happens here for a general C? Now, here the market clearing condition, it's interesting what happens. Is that the condition that the sum of those D's for the players is equal to C, this is amount of resistance on the market. And what it means exactly, if we substitute the D is theta divided by p to the power of 1 over c, so we find the p, and then whenever theta is not the zero vector, so the sum is not 0, what a user receives is again theta of that user time p to the power of minus 1 over c, and we found p here. Now 1 over c is exactly something which cancels this c, and minus means we divide by that. So it's exactly theta divided by the sum times c. That's exactly the share we got in our mechanism. So for any c, not only for c equals to 1, actually the share you receive when you beat theta is this proportion of your share relative to the others. For any c, that's quite surprising. So the allocations are proportional to the bits for any c. This is really surprising, in my opinion. And this is a special case. So not only is that so, but actually we'll prove that any mechanism in this deep calligraphic D, which is not so small a class, it's quite a large class, intuitively speaking, but any mechanism there yields the proportional allocation. So only the price can differ. But the proportional allocation actually is for any mechanism. We call only our allocation we call proportional, but actually any allocation returns this proportion in this any allocation in this calligraphic D. Since simply that our allocation, which actually makes you pay what you bid, is also, or in other words, it makes you pay what you get times the price. it's also uh, that the price is reasonable. But actually, area allocation here is proportional allocation. That's quite surprising. So we actually will prove something more general for anything in calligraphy. That's going to be one of the things which we are now prove. Now, another thing we want to talk about is what is the efficiency of various mechanisms. So calligraphy contains many mechanisms. Already this class we defined now contains continuum many mechanisms for any C which is at least one. So yeah, they all give something similar as we see, at least for those we see that they get the same. The users always get a proportional share. The price is different, so the mechanism is different. The question is which mechanisms are the best from the point of view of the social welfare? Which mechanisms eventually optimize the total value of the use? And what we are going to show is actually the mechanism we start with is optimum. Actually, that's pretty much the only one. That's also going to be one of the things. So first of all, we define this general price of anarchy. So the question is what is the least ratio of the utility in the equilibrium to the optimum utility, which can be achieved when we don't care about the stability, when we just solve this system program. I remind you that it's simply any allocation which allocates at most what we have, any feasible allocation. And formally, what we want to see is that for any mechanism, you define the price of anarchy of that mechanism. So that, of course, is actually a price of anarchy across many games. So I look at the worst, which can be, I look at the intimum. So that's actually the best, because the worst in the case of price of anarchy, in this case, is something larger. I'm looking here at the infinite. So what is the best case among all those games when you vary the amount of resource you have C, the number of players you have capital R, the valuation functions? What is the among those? You look at the smallest price of anarchy. Excuse me, no. Okay. Okay, I apologize. I got confused. They don't divide the price. Divide the price of anarchy as usual. That's it. Okay. By the way, that's a nice example. Nothing important, but the book is written by various authors, and each one has a little bit different definitions. They don't always tell it explicitly. Now, actually, here they do. So that's my mistake that I didn't know this, but now I'm telling you. So look, they don't look at the price of anarchy, which is the highest amount divided by the lowest amount. So that at least one, and the larger the more is the gap. So the price of anarchy is worse, so to speak, when it's large. Here they actually look at the smallest amount, the value under this mechanism, and they sum it all the players, so the total value the players get in the mechanism divided in an equilibrium, requires the vector equilibrium in this game of price anticipated users, divided by the optimum. Because we look at all the possible solutions for system, which is simply any allocation, and we look at the worst case when what you get is the smallest relative to what you could have got. So that's an equilibrium. That's a price of the same logic as in the definition of price of anarchy. Simply here the smaller the stronger the anarchy, so to speak. The smaller the stronger the anarchy. And then also look at the worst case. All the C or sizes of resource C of all the sizes of of all the numbers of players R, capital R, and of all the valuation. What's the worst case? Not only in a given game, what's the worst equilibrium, but we'll see there is actually one. But what's the worst case of all those games? Now, and that's what is defined, of course, only if the Nash equilibrium is not empty. Otherwise, we say tell it's minus infinity. Now, we need to justify why we may divide by the sum of the valuations in a solution to system. And what they say is, because the interesting solutions, those who can get us closer to infinity, they're optimal. And since these functions are strictly increasing and non-negative, so that for any c greater than 0, when the set of the research to divide is greater than 0, and it's going to be strictly positive. Because already when you don't give them anything, it's non-negative. It's strictly increasing when you have something to divide, at least one is strictly positive. So the sum in an optimum solution will be strictly positive. So you are allowed to divide by what you divide. Okay, after many words, that's the definition of the worst price of anarchy among all those games. And then that's the main result in this characterization session, where we are going to exactly characterize what's going on here, and we'll show also the best price of anarchy possible here. So the best situation for society, in other words, is in the mechanism we start. So it's not only intuitively a nice mechanism, but it will also be now provably nice mechanism. So what we prove? That's quite a complicated theorem, but I'll take you through that simply. So for any smooth market clearing mechanism in graphic D, two things hold. First, there exists a competitive equilibrium theta. And for any such equilibrium, the resulting share of the resulting vector of shares is an optimum solution to the so basically every equilibrium is optimal. The second thing, there exists a function from the positive reals to the positive reals such that which is also concave, strictly increasing, differentiable, and invertible, so kind of a nice function from the positive to the positive. So let's say what can be, for example, such a function. F of x equals to x. Concave, strictly increasing, differentiable, and invertible. And of course, there are other functions like log, also divided over those non strictly positive reals, and it's also concave, strictly increasing, differentiable, and invertible. Now, such that this d is equal to theta divided by p. So it's not that you always have, like in our case, that it's theta divided by p, or that, like in the example we have seen, that it's theta divided by p to the power of 1 over c, but there is always a function, which is kind of a nice function from the positives to the positive. Such that this theta divided by this function. That's all you have. The last thing, that the least share you can get, the share you get is at most, in the worst case, at most 3/4. So you lose at least a quarter, at least 25%. And the equality here, or the best mechanism, in the sense that it loses the least, takes place even only if the mechanism is simply some constant times what we have. Theta divided by p. It should be by p. Not by 0, of course. Typo. let me fix that. Divided by now. Just pay attention again because they define the price of anarchy as something which is gets smaller when it's worse, when there is a huge large difference between equilibrium and the optimum. Being larger is better. That's exactly the share you get. So we say equality taking place, it means that the best option, the higher price of anarchy in this, it is not called price of anarchy, actually it's good, not called price, but it's the same as simply divided 1 over. The best case is actually when we have our mechanism, our actual constant. Now, immediately noted, the first two conditions characterize the mechanism. D in particular, so the first says about that it has a competitive equilibrium which optimally solves the system. Now, in particular, since the four, so many typos after all these corrections. Since 4 non-zero vectors and any smooth market clearing, the sum of those shares has to be exactly C. Condition 2 implies you can just replace D with theta divided by B of P. And then it means that B of P has to be sum of theta divided by C. And when the share you get actually, it's theta divided by B of P. When B of P is this, it's basically theta divided by sum of theta times C. And here I have a latex problem. And I need to fix that. So I have the sum fraction theta. Okay, that seems to be the right way. But basically I'm shown, and I apologize for these typos, that any mechanism, because of this number 2, actually we now have shown any mechanism, yes, well, Python will give you the proportional share. That's so cool. So any mechanism in this similarly large class, indeed a large class, D, calligraphic D, because of this characterization and because of number 2 actually, will give you a proportional share. All the prices will be different. Price can be different, but they always have to be certain, but according to those rules, but they can differ. But the share will be always proportional. And here also another thing. So yeah, because the conditions characterize the mechanism, and again here there is the same typo. Resist somehow. Now, and the share is always proportional. Now, so basically the share is always proportional to the bit. Only the price is different. Now the proportional allocation here will be proven because it will be based, we have now shown it's based on 2, which will be now proven. So it's not something we presuppose. It's something we suppose, you can say in the definition of the normal proportional. So in there, you can say that we just assume that the D is your bit divided by the price. But there you can also start with that this is proportional. That's one of the ways we started. But here we just proved that it's proportional. So we didn't know that, but we now prove that any mechanism from this graphic D yields a proportional allocation. That's a cool thing with characterization. Another cool thing is that our mechanism is exactly the best one from the point of view of the proportional one. Price of anarchy, or the opposite of the price of the inverse of price of anarchy, rho is the best. Okay, so now let's prove the theorem. Now the proof is quite long. Now don't worry, because we're going to avoid most of the technical details. Of course, for the exam, you don't need to know things you're not shown here. You in particular don't need to know the technical details of such a proof. It's good for you to know whatever you can, but what you need to know is the main steps. That's enough that you know the main steps. And so I think if you now follow me, it will help you to kind of grease to improve your knowledge. But the main thing you need to know exactly for the exam is only the main step of it. Because this is a long proof, which is quite technical. If you see what I do in the group, they do a bit less than I do in some points, a bit more in some other points. It's always very technical whenever they go to something longer. And that's also not a complete proof. So to be complete, you also need to write, to work it out sometimes even more into detail. So that's definitely a very technical proof. That's not what we are doing in this course, and don't have this time for that. But so don't worry about that proof, but try to enjoy that, because it's possible to enjoy those considerations, how you manage to prove such cool things and strong things for some seemingly weak assumptions. And just remember the main idea. That's the main point. You remember each one of the steps we're going now to show. Now, the proof fixes a D, a market clearing. We call D a market clearing mechanism. So the proof fixes a proof market clearing mechanism, and then proceeds in the following step. Actually, it has several other steps, which are just technical steps. I'll at least mention them. But those are the main steps. So it just proves that there exists a B such that D is theta divided by B, some function B. Then it proves this first item, that the existence, the first item is the theorem. There exists an optimum competitive equilibrium, and that is shown from condition 3 in the definition of D. I remind you that is onto condition, so that any share can be achieved by an appropriate bid for any price. For any price, any share can be achieved by the appropriate. So we also can, in that way, achieve an competitive equilibrium, which is optimal. Now the properties, all of them are. The properties of function B are derived, because we want to show that B is not only that there exists such a B, but we also want to show that B is concave, strictly increasing, differentiable, inverted. So then we also are done with the second. So we start the second part, then we do the first part, and we finish the second part. Now we are left with the third part. First, prove that there exists actually a unique Nash equilibrium. Then we prove an upper bound on rho, and then we show that any mechanism besides the proportional allocation has the worst case, which is worse than the worst, whereas the proportional allocation has exactly. Okay, that's the plan. Now let's dive into the proof. So step 1. In each technical step, this technical step is a technical step. It's not something we have listed now. We prove that price taken users pair is concave. What it means is that when you look at what a price taken user gets, so for any value function or for any price, the price the price taken user is the value for what the user gets. When you assume that you have a price, you don't see the dependency on those two bits, and minus the price you pay, which is the price again, the given price, times what you get. Because in the language, in the case of the original mechanism, it's simply the value of your share of the raw resource times what you bid. What we now prove is that that thing is concave. Now we've shown that when we look at the mechanism, at the original mechanism, and when we look at the bid users who are not price taken but rather price anticipating, then that is concave. That's what we shown. Strictly concave. Now we need to show that it's also concave in this general case and for price taking. Now the idea is to use this fact to prove that we know for price taking use. Now we know for price taking users you've already shown that not only for the hour case but in general that is concave for price taking users. And now we are going to show that also for price. Excuse me. We know it for price anticipating. And now we are going to use limit to show it for price taking. It's a type here. We know it for price anticipating. Let me fix the typo. Now, how we show it for price anticipating users. That's our assumption, of course. That the price anticipating users pair is concave. That's the case. We've proven it's the case for our mechanism. It also can be shown to be the case for this more general mechanism when we look at the theta divided by p to the power 1 over c. But that's also what we assume. That's simply an assumption. That's only we work with such mechanisms. Now, assuming that for price anticipating users, we're going to prove it for price taking users using limits for large capacity. Well, that's the idea. That's enough to know for this kind of proof because it's too long. But now let's see what exactly they did. So since D has a unique market clearing price, that has to be monotonic. For any fixed theta, it's monotonic in the positive piece. E values of P. Because otherwise it will not be unique. Now, continuity implies that actually for any theta, not only that for any theta, it's monotonic, but maybe for one theta is monotonic increasing, for the other theta is monotonic decreasing. What we actually have is for either for all the theta, it's non-decreasing or it's non-increasing because of continuity. We cannot do it for some theta is like that, some theta is like that, because then there should be something in between which we don't have. Now, so that's one of the things. Now, knowing that, fix some mu will be working for price and some bit theta. Let the capacity in the R system, so system of R users, be R times what D gives from mu and theta. And consider the limit when the number of users goes to infinity. When the users 2 to R, so goes besides 1, bit theta, and user 1 bit some other theta prime, maybe then the market clearing limit what will it be? It will show that regardless what user 1 bit, the price has to be mu, because what user 1 gets is of course this price, the d of this price theta 1. For the rest of the user bit theta, the total resource which they all have to get is r times d of mu theta. Therefore, from the equality, in the limit, when the number of u's goes to infinity, the price goes to theta. To mu, to mu. And here we use the monotonicity in P. Now, because we know this thing, the price goes there. One second. Price anticipating. Since we know that thing, there is this limit, and we know that price anticipating users do have a concave utility function as a function of their bits. It again, it's a technical move, but it can be shown that it implies that also a price taking user has a concave pair as a function of the setup. Okay, so that's what we showed. This price taking user has a concave pair. That was the first technical step. Now, finally move to something non-technical. We need to show there exists beta, function beta, such that d of p of theta is theta divided by b of the price, beta of the price. Well, b, of course, it's not beta. What happens to me? I apologize for calling capital B beta. Since there has been no beta here, I hope you've not got confused. So how do we do that? Again, we see the main ideas here. Whenever it goes technical, I usually omit it. So actually, you see the kind of the nicest, the tasty parts of this huge cake, which is proof. So the idea is use concavity, which you already seen, and we now see something is convex and concave, and it will imply actually that it has to be linear. Well, affine, linear plus a constant. So first, by the first step, price taking price path that is concave in theta. Now, V that works for all the V's, for any V in calligraphic V, for any V. Therefore, by choosing sometimes very steep linear V, sometimes very non-steep, so close to being a horizontal linear V, we'll eventually conclude that for one case D has to be concave, for another case D has to be convex in theta for any fixed price. And since something is convex and concave, even only if it's affine, then so these are fine for any fixed positive price. So there are constants A and B. Let's just call them A and B. Of course, small b does not have anything to do with the capital B. I just use that for convenience. Such that d theta is A theta plus B. Now we just have it's a very simple now, like it's cool. Condition 4, it says that d is always non-negative. What does it imply? That both A and B has to be non-negative. Because if A is negative, of course, at some point get negative. For large theta, A has to be non-negative. And for theta equal to 0, the value is equal to B, so B has to be non-negative. So they both have to be non-negative. The condition 3, which tells that for any price, we can give any result by bidding the property. What it tells us is that first A has to be strictly positive, because if A was negative, we would not be able to we would not be able to, excuse me, a cannot be negative. We already have shown it's non-negative. If a was 0, we would not be able to get more than just always b, so it has to be strictly positive. Now b cannot be anything positive, because if b had been anything positive, it would mean that we never get 0. So, or definitely we not get anything which is smaller than b. So b has to be 0. So, but simply like you look at those conditions 4 and 3 in the definition of calligraphic D of the set of mechanisms. You look at, you see them 4 and 3. Just don't have space to show it here, but I can actually quickly go back there. Yes, this class, it contains all the smooth market spreading mechanisms, which are also so 3 is condition that you can get anything you want, and 4 is a condition of non-negative. Non-negative. Good. So eventually get that a is positive, b is 0. So d of theta is d is simply something positive times theta. Yeah, I think I've made a typo again, or no. D is something positive times theta. Yes, okay. So that positive, let's call it b of p. B of p is going to be a times. So for some, we've proven what we wanted to prove here. There exists a function b. There exists something. It depends only on p. So d is theta divided by d. And from the discussion above, I mean that it already implies, even before knowing that b is concave, it already implies that any mechanism in this graphic D allocates proportional to the b. Only the prices will be. Next step. Next, in this step, we prove that for any given C capacity that we use, number of users, and the vector of utilities, I mean of the vector of relations, there exists a competitive equilibrium, which is also optimum. Now, I won't do it because it's quite technical. Even the book does not do it completely. The idea is to employ this condition of being able to achieve anything by an appropriate bit in definition D. Then you can choose, a user can choose the optimum quantity by the appropriate bit, so that eventually allows you to choose something which will be an optimum and competitive equilibrium, and it will also be optimum. So we omit the details, but we've proven already point 1 theorem. That was point 1. Now, for point 2, we still need to prove the properties of this function beta b. But now we need a technical step. So let's now make a small technical detour. Okay, so another technical thing is that, I mean, they're technical, but they're not like extremely separate from what we are doing, of course. So you can see that there is something here to prove the concavity of some important function. So in this technical step, prove that for any number of players, which is this one, and for any bit of the others besides r, that is, the function of what player r gets when r anticipates that the price depends on what he bids. Of course, here it should be PD of theta. It's not exactly what I needed to type. So it's like that. That's exactly okay. What will I get? R get when we didn't theta R when the R is such that eventually it's the vector theta. And the minus of what she pays. Or in other words, if you look at this only as adding, that's what she pays. If you just remove that, what she gets times the price with minus. And of course, that all depends on the price anticipated. So what she gets and the function of what she paid, they're both concave in the positive theta r, and the rest don't be zero. So then you only look at positive theta r's, and when the rest, the bits of the others are not the zero vector, then you can look at any non-negative. And the idea to use the concavity of price of anticipating pairs, while also, as before, taking linear value function, it's very large or very small slope, and eventually you get that it needs to be what you want. It's a technical thing, we omit that further. Now, finally, we want to finish the second step. And remember that we've done the first step about the existence of the optimum, the competitive equilibrium, which are optimal. Now, the second step, let's go back. I mean, the second extreme, second point. It was not the second step, I think, but the second point was actually the second step by chance. We prove that there exists a function b such that v of t comma theta is equal to theta divided by b of the price. It's not like you can tell that it's theta divided by the price, or even theta divided by the price of some power like we had, but it's theta divided by some function. And what is that to say? That this function is increasing and so all those properties we wanted to do. It's concave, strictly increasing, differentiable, and invertible. Now, before we prove that and finish thereby the second part theorem, I need to make a small clarification because there is this confusion maybe with parameters. So here, what we have, we've proven that d for any fixed p, d is an affine function of theta. Moreover, d is simply some strictly positive number times theta. But this number, which we call the b of p, is not itself necessarily an affine function of p. So we have not proven here that b is like affine or something. It is not necessarily affine. That's an important thing. That by this proof that we have just said that we can, for any fixed p, we can say that d of theta is some number times theta. But the dependence of that number of p, which we call b of p, is not clear yet. That's what we're going to show now. And so that invertible differentiable strictly increasing and concave. Really a nice bet. B. Now function b is on 0 from infinity because we have shown that it's the sum of the bits time divided by c. That's the total capacity which we share. And the letter, of course, can take any value, any positive value. Now, since it's onto, since the solvent price is unique, it's also 1-to-1. Now, being 1-to-1 and onto, in other words, the bijection, it means that it's invertible. It's actually exactly the same as saying it's invertible. Now, The second property, we have shown it's invertible. It's differentiable because this is differentiable. The third property, or the third method, we need now show it's strictly increasing and concave. That's what is left here. Now, how we do that? We show it by showing that it's differentiable because it's differentiable. Inverse f, p it's called, not f, p, the Greek letter, is strictly increasing and convex. So it's strictly the inverse, which we know it exists, which have shown it exists. We have shown that, and it's differential because b is differentiable and that. So we don't show, but it's a differentiable function. Now we need to show that this inverse is strictly increasing and convex. That will imply that b is strictly increasing and concave. How do we do that? You define the function w as what you pay for what you get, which is p is the inverse of b of what you have, not what you have, but simply that's what we know for b. So p is the inverse of b on that right hand side. So we write it p of the sum of p divided by c instead of the price. And the d we have shown already exactly the proportional share. Now we have shown that the left hand side is convex in the positive theta. Therefore, technically it's also possible to show now that the p is convex. And the only remaining thing is to show that it's strictly increased. It's also technical and we omit it. So we have proven that b is really nice. And now we are left with the third part. Let me just remind you the third part. The theorem is quite long. That's basically the efficiency. That it's never better than 3 or 4, that an equilibrium, at least in the worst case, it's never better than 3 or 4. And it's equally true only if that d is exactly some constant times theta divided by that. Okay, and already I've written divided by 0. I need to include that. You understand I meant divided. Was it actually be divided by 2? So let's finish that. First of all, we prove that given any something which we use to the size of the resource, the number of players, don't confuse R as number of players because the resource is called capacity here, so I don't think it's a good name. But anyway, capacity as the resource R as number of players, it's nice a natural number, one or more in general. And the vector v is the vector of the value functions. Theta is an Nash equilibrium if and only if the following conditions hold. And that's something which is similar to what we did once. Quite technical, but we just need to at least know to formulate it. So there exist at least 2 players where the theta is not 0, that we know. We know that for another case, which is simpler, but we also can make in general. Then there exists a non-zero, non-negative vector d and a positive mu, such that mu is kind of the price. So mu times d is exactly the bit. So the bit is, so what you get is the bit divided by mu. For any player, the sum of the d's is exactly the resource. And there is a condition, it's quite confusing. where dr denotes what player gets according to d. U is exactly the thing for the price because it's the sum of the bits divided by the capacity. And T is the price solution. Now again, that's something which is, I don't want you to understand this exactly. Understand that we have this as the formulation, and there exists a unique Nash equilibrium. Okay, so okay, I apologize. I've actually, in this case, I've confused you. And again, I need to improve the slide, but so I think I'll do it now because it will make it clear, more clear to understand. So, a Nash equilibrium, that is Nash equilibrium if and only if these two elements are not zero, it's positive, that is non-negative. There is d vector d, which is non-negative and non-zero, and mu positive and positive u, such that we have those conditions. Now, if that's the case, again, these conditions are quite confusing, but if that's the case, then this d mentioned here that there exists a d, a vector d, then it's defined as simply what this d tells us, what this mechanism tells us. Mu is defined as the price should be defined based on the theta and the c, and P is defined as again the price. Now, that's so. If that's the case, then that's also there is a unique Nash equilibrium. So if there is a Nash equilibrium, it's unique. Now the idea is to prove it. We don't of course do it. It's too long to do it. Is to connect the Nash equilibrium conditions to the optimality of an optimization problem. It also will be, that's why also it will be unique because it will be Nash equilibrium. And we did such things that it's those first order conditions, and then we look at this Lagrange optimization and use method of Lagrange multipliers, and then we had this connection. It was highly technical, not extremely illuminating game theoretically, but it was simply helping us to say that something optimizes some optimization problem. If it was the original problem we called system, where we just basically tell that we want to share the resource in the best possible way, then we also claim that then we often had that optimum for that system. So when we said that Nash equilibrium is only if it's optimum, sometimes once we got that it was the unique solution, it was nice that it was unique, but it was a unique solution for another system which we call game, and then it was not optimum, but it was still proved existence and uniqueness. So we had this, and a similar thing we can do here. And again, this technical, we don't do it here. But we have this nice characterization of Nash equilibrium to the extent we can call it nice. Then next step, finally, we're almost there. So in this step, we just prove that for any epsilon, there exists something which for any Nash equilibrium, but the equilibrium sum of values is not more than 3 or 4 plus epsilon times the optimum. No equilibrium can be better than 3/4 plus epsilon, but that's for any epsilon. So that's what we need. That's exactly what we need. And the idea is to find the Nash equilibrium using the conditions from the previous step, and then we can find a Nash equilibrium which also fulfills those requirements, and we omit the technical details. You can look it up in the if you want. Don't have to. Now the last step is that now we need to show that for any mechanism besides the proportional allocation, the worst case actually will be strictly smaller than 3 or 4 than 3/4. While the proportional allocation is exactly 2. And again, we don't do the technique here. The idea is to use the linearity of this function b in the case of proportional allocation to show that it's exactly 3/4. And if it's not linear, then it's strictly smaller. And we omit the details. But we have thereby proven the third part of the theorem. And the theorem, up to those technical omissions, is fully proven. Now let us look again at the nice theorem. So we've first shown that there exists a competitive equilibrium, which is also optimum. Second, that any smooth market clearing mechanism D has to be just theta divided by some function of p, while this function is concave, strictly increasing differentiable invertible. And that implied also that the share that you get is always this proportional share to your bid. Only the prices may differ. And the final part is the efficiency. Okay, so let's now go to the remarks. So we have proven that for any D mechanisms D in this set calligraphic D, it allocates proportional to a bit, so only the prices may differ. The efficiency loss is minimum when actually the price is the bit. In this mechanism, we call proportional allocation. So it's not the only mechanism with proportional allocation. It's actually unique among those in calligraphic D, not in how it allocates, but rather in what it asks you to pay. Now, but we still call it proportional allocation if you want to name the mechanism. Now, when the theta vector theta is 0, the market clearing price may not exist, as we said. We just define the utility of the user as minus infinity. But another solution, as we said before, as we already saw it, would be actually to simply tell, because that anyhow the share you get is 0 if all the PRI is made with 0. Excuse me, if you bid 0, you get share 0. If you bid 0, don't care what the others. As long as you bid 0, you get 0. Then the price, which fits when everyone bids 0, something which is not defined by the equation, but will define it to be 0. And that it will imply that the utility of anyone, when the players that beat everyone bid 0, it's simply what you get, and everyone gets 0, minus, well, the value of what you get, the value of 0, minus what you pay. What do you pay here? The price times what you get. Since the price is 0 and you get 0, you pay 0. So that's exactly the utility, is the value of getting nothing. That's what we also did before we looked at this mechanism in general. So that's another way. And the main result can still be shown to hold under this definition. So as we said, it doesn't matter. Of course, a lot of techniques probably to see it again, but it can still be shown to hold. So we have basically finished the idea of the mechanisms of that kind, in the sense that we said, okay, we said we had this mechanism which was fine, was not perfect, when players didn't anticipate prices, when they just took them as given, then it was actually very good, it was optimum. When players did anticipate the price, so they just played the game, they optimized what they beat, then it would not be optimum, but we managed to bind to found the price of anarchy, and now we actually have shown the price of anarchy. All this worse than what we have there, and actually what we have there is the only optimum case if we restrict ourselves to mechanisms in this calligraphy. So we have actually got surprisingly nice, simple, you may say, description of this calligraphic thing.